Hello, welcome to ISAT430 Materials and Manufacturing Processes. This is the lecture 11, Property Enhancing and Surface Processing Operations. So for this lecture, mainly we are talking about how do we manipulate properties of substrate materials as well as surface of the materials. First, heat treatment of metals. So in this course or in this lecture, mainly we're focusing on the metals because metals are most common processes are and also the operations that we see in the in industry. And also mainly the heat treatment are related to the metal because if you remember in the phase diagram, when we are increasing the temperature or changing the temperature, the structures, material structures, will actually change. So this is how we manipulate the properties with metals. It can also be performed on some other materials, for example, glass and ceramics, as well as some powder metals. And heat treatment can actually be performed at different stages of manufacturing process. For example, at the raw material before everything is processed, we can soften the metal before forming, so it can be easily formed to reduce the energy consumption and also some of the cost. And also it can be performed during the forming process to relieve some of the strain hardening. Also, it can be performed at the end of the manufacturing process or near the end of the manufacturing process to increase the strength and also and harden the metal. These are some of the main heat treatment methods. Includes kneading, martensite formation in steel, tempering of martensite, and precipitation hardening, and also surface hardening. Now we're going to look at it one by one. First, kneading. So kneading is a heating and soaking a metal at a suitable temperature for a certain time and then slowly cooling down. So the reason for kneading includes, we can reduce the hardness and also brittleness because, if we have a really rapid cool down from a really high temperature, what happens is actually it increases the hardness and also brittleness of the material. So in order to to reduce those hardness and brittleness, we actually have to cool down in a slowly pace. And also, for kneading, we can use the kneading process to achieve the desired mechanical properties. And for example, soften the metals, before machining or during forming. And also release the residual stresses by shaping. So during a kneading, it actually can be performed at two different cooling speed. So one is the slow cooling and the other one is the faster cooling. For slow cooling, it is called a full annealing, while for faster cooling rates, it's called normalizing. And for the two processes, actually the property material will also be different. For the first one, full annealing, it produces a coarse perlite, but for normalizing, it actually results in a fine perlite, higher strength and hardness but lower ductility. So these are two the difference between the two. And so this is the phase diagram, as we seen before when we were talking about this. So it's the carbon and iron phase diagram, and so this diagram basically shows the phases of iron and also iron carbide under the equilibrium condition. You see there are different regions And also these are the forms of the structures at different temperatures, and also the carbon percentage. And so this is kind of a guideline for us to perform heat treatment in terms of determining what kind of temperature it should be, and also what percent of the carbon we want. So look at this picture. So this diagram mainly shows, for it's a temperature versus time graph. What it shows is, with a certain steel, and if you increase temperature or reduce the temperature, and what happens to the structure at different phases. For example, you can see the dashed line, so the possible cooling trajectory. So the top there, that is the austenite structure of the material, and if we reduce or cool the material at a rapid speed, following the cooling trajectory, and what happens, it will go to go eventually to a room temperature, and in the room temperature it will create a martensite structure of the material. So pay attention to to the curves. I see the start finish. There are different regions. And for the possible cooling trajectories, you can see it is not touching the curve. That is, you can see the nose curve, because if the possible cooling trajectory, the line actually get into that curve or touches the curve, actually it will form a different phase of the material, and then we'll lose our purpose, because if we want to form our martensite material or structure, we actually want to cool it down directly from austenite, right? Have a rapid cooling to room temperature immediately before touching that curve, and that curve is called TDT curve. Then we talked about martensite. What is martensite? So martensite, you can see from this picture, there are different different structures for the steel carbon phases at different times, and also the temperatures. And the austenite is a unique phase, actually consisting of iron carbon solution. The composition is the same as austenite, which is derived, right? So during the process, the face center cubic structure, you could say austenite, that is a face center structure. Austenite is transformed, right? When we're forming the martensite, so that kind of structure is transformed into a body-centered tetragonal structure of martensite. You can see at the bottom there, that's the martensite structure. You can see that graph. And so the extreme hardness of the martensite actually results from the lattice strain created by the carbon atoms trapped in the body center tetragonal structure. So this is how it provides a barrier to slip. And the forming of the martensite actually includes two steps. First one is we want to make sure that we heat up material to temperature that is for forming of our austenite. Usually that's above 723 Celsius, which is 1,333 Fahrenheit. And let it stay for a while until it's fully converted into an austenite structure, or partially to austenite structure. Then will have quenching process that is to cool the austenite rapidly, enough to avoid passing through the nodes of the TDT curve. Let's see the TDT curve, avoid passing through that curve. So this is the fast cooling to a room temperature. So this is how we heat treatment to form martensite. So after forming the martensite, the structure we formed is actually a body-centered tetragonal structure. You can see the left figure, and so this structure has a high brittleness, and also toughness is also very low, but in a lot of applications when we're using steels, we actually want to reduce those brittleness and also increase the toughness. And so usually after the two steps, we also have a tempering process. So the tempering process is to reduce those brittleness and also increase the toughness. And how do we do that? After we form this martensite structure, we will actually gonna heat up the material again, but at a much lower temperature, right? So this at the tempering temperature, usually that's below the eutectic point. Having been soaked in the temperature for a while, for example, an hour, and then followed by a slow cooling, because during the slow cooling, we actually can relieve the stresses. So the reason they are actually gonna reduce the brittleness and increase toughness is because during this process they actually can create some precipitation of the very fine carbide particles from the martensite are in carbon solution. And the structure will be changed from the body-centered tetragonal to a body-centered cubic structure. You can see the difference between the two structures, and the new structure is usually called a tempered martensite. Next, a concept is called a hardenability. So the hardenability mainly is talking about the depths depths below the quench the surface, they can be hardened. So for some of the materials, it can be hardened at a higher depths, but some of the material can be hardened at a really lower depths. So this is about hardenability. So you want to make sure it's it's different with the hardness, right? Hardenability is not talking about hardness. And the hardenability actually can be increased by alloying some of the elements. For example, chromium, magnesium, or molybdenum. So how they work is that by adding those elements into the material, it actually gonna move the TDT curve to the right. So which means, remember the idea is we do not want our trajectory, that's gonna fast cooling trajectory curve touch the nodes of the TDT curve. So, but if we move the TDT curve to the right, we actually got more time to cool it down. Actually, we will, reduce it, probably achieve the similar purpose to the tempering. So this is how how the hardenability works. And precipitation hardening. So it's a heat treatment that precipitates the fine particles that block the movement of dislocations, and then to strengthen and harden the metal. And this is also a principal heat treatment for strengthening alloys of aluminum, copper, magnesium, nickel, and some other non-ferrous metals. But also it can also strengthen the steel alloys, because some of the steel alloys actually cannot form martensite by using heat treatment. So the sequence of precipitation hardening is kind of actually similar to the heat treatment we talked about before. Also have two different. You have several phases or steps. First one is the solution treatment. We heat up the material to a temperature that's Ts, and then we have quenching, which is fast cooling of the material to a room temperature, and then we're gonna lift up the temperature again to precipitation treatment, and then slowly cool down the material to achieve that desired properties. And you can also see from the phase diagram how the temperature works from Ts. First, the Ts is at the alpha stage or phase. Heat up material to alpha phase, and then quickly cool down to the room temperature, will form a solvous phase. And then we heat up the temperature again to a TP, right? So this is and then slowly cool down back to the room temperature. During this process, especially precipitation treatment, it will cause the precipitation of fine particles of the beta phase, at room temperature. Next one is surface hardening. So surface hardening means we are only treating the surface of the materials, and it is also a thermochemical treatment method. So because we are only treating the surface, so it's often called case hardening. Some of the common treatments are carbonizing, nitriding, and carbon nitriding. Then we're gonna talk about one by one. And usually those kind of treatments are applied to low carbon steel parts, so they can achieve hard, wear resistance outer shell, so it also retain a tough inner core. First, carbonizing. So carbonizing means we want to diffuse carbon into the surface of the material. So in order to do that, we're going to put the material into a carbon-rich environment, and also make sure we heat up the material at a certain temperature so the carbon atoms can be diffused into the surface. And carbonizing is also a very common surface hardening treatment. Now let's look at one video about this. All right. Next one is nitriding. So nitriding is a treatment. The nitrogen is actually diffused into the surface of the alloy materials. But for this process, there's we can produce a thin hard casing that is without quenching. Usually the temperature it's carried out at around 500 degrees Celsius or 950 degrees Fahrenheit. And for nitriding, the hardness can usually increase up to 70.
When you hear the call of the wild, answer with a pair of Skechers. Waterproof, insulated.
All right, so that's nitriding. Next one is chromizing. So chromizing, so mainly we are diffusing chromium into the base metal. Also, usually it is applied to low carbon steels, and so the casing is not only hardened and also not only hard but also it's wear resistant because chromium is kind of a wear resistant element. All right, so these are the quiz questions. Next, let's look at another part of the lecture, which is surface processing operations. And so there are two main processes for cleaning the work surfaces. Either they are chemical cleaning or mechanical cleaning. So chemical cleaning means where we use chemicals to remove some unwanted contaminants from the work surface. Mechanical cleaning means we are removing the contaminants using some mechanical operations, right? And the reason we need to clean the surface or to process the surface again, either we want to prepare the surface for subsequent processes, for example coatings or adhesive bondings, or we want to increase the hygiene conditions for workers or customers, or remove some contaminants that might chemically react with the surface or enhance the appearance or performance of the product. And when we are choosing a cleaning method of the surface, there are several factors we need to consider. For example, what kind of contaminant you need to be removed, and what degrees of the cleanliness that is needed, right? And also what kind of substrate material you are dealing with, and also what kind of purpose of cleaning. Some of the environmental and safety factors, also chemical versus mechanical. Also the size and the geometry of the part. Some of the cleaning methods might be more fit to smaller size, while some of the method can do very complex geometries. So also these are the factors you want to consider in choosing cleaning or selecting a cleaning method. Of course, all these different cleaning methods with different cost as well. Some of the chemical cleaning processes include alkaline, emulsion cleaning, solvent cleaning, acid cleaning, and also ultrasonic cleaning. And for the mechanical cleaning processes, we have blast finishing, sharpening, tumbling, vibratory finishing, and also mass finishing. So there are these are some of the videos we're gonna we'll quickly go through those videos and give you an overview of all these methods. You can see during this process, there are a lot of abrasive materials actually interact with the surface of all these parts, and this is how it actually removes or cleans the surface of the parts. Next, shot peening.
Curtiss-Wright Surface Technologies provides highly engineered processes worldwide which improve the life, strength and performance of critical components in a wide range of markets. Metal Improvement Company, a business unit of Curtiss-Wright Surface Technologies, is a recognized leader in surface treatments and the application of controlled shot peening. The application of controlled shot peening improves performance, reduces maintenance, and provides a cost-effective solution to premature failure in critical components. Shot peening is a method of inducing residual compressive stress into the component by bombarding the surface with high-quality spherical media in a controlled operation. The media can be steel, ceramic, or glass, and each piece acts like a tiny peening hammer, producing a small indentation in the surface. The application locally yields the material, inducing beneficial residual compressive stress, the characteristics of which are dependent on the base material and component design. At the same time, unwanted tensile stresses are removed. The proven results from controlled shot peening show a dramatic beneficial effect on both the life and strength of components, welds and materials, making the material resistant to fatigue, fretting and stress corrosion cracking. Metal Improvement Company has over 75 divisions worldwide.
Next, tumbling. Laboratory finishing.
CB rotary vibrators are truly universal mass finishing machines, which can be used for a wide range of workpieces and surface finishing objectives. Their applications range from intensive deburring and edge radiusing all the way to mirror image polishing. In other words, from aggressive grinding to pre-plate surface finishes. The oscillating movement of the processing bowl created by the vibratory drive system causes constant rubbing between the workpieces and the grinding media. This leads to the removal of material, especially from the workpiece edges. The workpieces determine the shape, size, and performance characteristics of the media that must be selected for a particular job. Water and compound are essential ingredients, not only for cleaning and passivating, but also pickling of the workpieces. They also help maintain the abrasivity of the media. The characteristic tumbling motion of the processing bowl is controlled by the quantity and setting of the imbalanced weights on the vibratory motor. Pushing and holding the button changes the motor's rotational direction and clears the ramp area from any media and workpieces. Clearing of the ramp area ensures that no workpieces or media get caught by the separation flap when it is lowered onto the ramp. When the button is released, the rotational direction of the motor changes back, allowing the mix of media and workpieces to rise to the screen deck level. workpieces made from carbon steel can be separated from the media with a magnetic belt separator. In this case, no separation screens are required. The finished workpieces and media are guided onto a polyurethane plate from where the media falls back into the processing bowl. The workpieces are picked up by the magnetic separator and pass over a demagnetizing zone integrated into the belt before they are transferred to the next manufacturing step.
Next one is mass finishing. All right. Another type of processes are to impregnate foreign items into the surface of a substrate. So it includes diffusion and also ion implantation. First, let's look at diffusion. So diffusion is a process that alternates the surface layers of the material by diffusing atoms of a different material, usually it's an element, into the surface. Usually it's at really high temperatures. So for this process, for the diffusion, the surface still has a large portion of substrate material. Well, for the ion implantation, actually it changes the chemical property of the surface. But for diffusion, it still has a large portion of substrate material. And so the diffused element has a maximum percentage at the surface and rapidly declines with the distance below the surface. So the further you get into the below the surface, actually the diffused element, the percentage will actually decreases. Some of the typical applications for this diffusion is metallurgy, processes, and also semiconductor manufacturing. So for some of the surface treatments that can increase the hardness and also wear resistance, for when we are using diffusion processes, it includes the carbonizing, nitriding, carbon nitriding, chromizing, and boronizing. These are all kind of diffusion process, and also surface treatments to increase the corrosion resistance and high temperature oxidation resistance. This include aluminizing and siliconizing, right? So aluminizing is to diffuse the aluminum into the carbon steel, alloy steels or superalloys, while siliconizing means diffusion of silicon into the steel surface. So ion implantation, this is the process that embedding the atoms of one foreign element or sometimes the more foreign element into the substrate surface using a high energy beam of ionized particles. So usually resulting to alternation of the chemistry and also physical properties of the layer near the substrate surface. And it produces a much thinner altered layer and different concentration profile than diffusion. So when we are using ion implantation instead of a diffusion, sometimes it's because it can be operated at a low temperature environment. And also we have the really good control of reproducibility of impurity penetration depths, and also the solubility when limits can be exceeded without precipitation of excess items. But for diffusion, usually there is a limit for solubility. And the applications for ion implantation, usually that's we are modifying the metal surfaces to improve properties, or we are fabricating the semiconductor devices that need special properties for the surfaces. So there's a video at the prior slide. You can watch the video by yourself. Next, plating. So plating is the coating process. Means that we're coating a thin metallic layer onto the surface of such substrate material. Usually the substrate should be metallic. So this way allowed although some of the methods are available to plate plastic and ceramic parts, but mainly when we're talking about plating, mainly we're talking about metallic materials. And so the processes include electroplating, electroforming, electroless plating, and hot dipping. Because electroplating is the most common process, so mainly we're talking about electroplating in this class. So electroplating is the actual electrolytic process in which the metal ions are in electrolyte solutions are deposited onto a cathode work part. So you can see in this setup, the work part is at the cathode, while the plating material, so which usually is another metal, is actually in the anode. And electrolyte, usually it's a solution of acids, bases or salts that can really conduct the current or conductivity should be pretty well. And what happens during the process is the metal atoms will travel from the anode to the cathode to the work part piece. So this is a setup for electroplating. Some common coating metals we really see in our life include zinc, nickel, tin, copper, chromium, and also some precious metals. They're always different purposes, right? For example, precious metals, they can increase the value or the appearance of those. While chromium, mainly where it has really good wear resistance property, right? Next one is coating. So coating is a process that a thin film of oxide, phosphate or chromate is formed, on a metallic surface, either by chemical or electrochemical reactions. So immersion and the spraying are the common methods of exposing the metal surface to the reacting chemicals. And some of the common metals treated are steel, zinc, aluminum, right? So if it is steel, usually that's also include galvanized steel. So some of the reasons for using conversion coating includes corrosion protection, right? Preparation for painting, wear resistance, decoration, finish, or increase electrical resistance of the surface, and also it permits the surface to better hold lubricants for metal forming processes. Let's look at two conversion coating processes. One is chemical conversion coating. So chemical that's for chemical reaction only. Let's look at this video. All right, for chemical conversion coatings, usually there are two common coatings. One is the phosphate coating, and the other one is the chromate coating. So it means that the surface of the metal surface gonna form different films depending on if it is the phosphate coating or chromate coating. If it is called phosphate coating, it will form a phosphate film, while the chromium coating will form chromate films. And of course, when we are doing those kind of coatings, we are actually exposing the metal surface into a phosphate salt or dilute phosphate acid. While if it's chromate coating, it will be the chromic acid or chromate salt. Next one, anodizing. So anodizing electronic a treatment that produces a stable oxide layer. So it's an oxide layer on a metallic surface. A very common material that it can be anodized is aluminum, but not all the not all the metals can be anodized. For example, copper cannot be anodized, it's not very good for anodizing. But aluminum is a very good material for anodizing. Same with magnesium. Some other metals can be anodized, for example, zinc, titanium. And during anodizing, so the dyes can be incorporated into the process, and then we create many different variety of colors. And so when we are using anodizing, usually that we are by adding or putting on different colors. That's for decorative purposes. Also, it can be used to for corrosion protection. So anodizing is also a very common process for coating of metals. All right, so that's all for today. These are the quiz questions for the second part of the lecture. And all right, that's it.